Good morning to all of you. Am I audible?
Yes, sir.
Okay. So today we would be start the topic of continue the topic of CDMA, and we have discussed up to the point of how to represent the data on this technique, CDMA technique, and that we have seen that data bit 0 has been represented as -1, data bit 1 is represented as +1, and if there is no data or any station is in the silence mode, so it would be represented as a 0. So on the basis of this data representation, we would be perform the encoding and decoding. So for this, we have to be take one of the example. Suppose there is a 4 stations that is sharing the link during 1 bit interval, and the procedure would be repeated for the additional intervals. So here we have assumed that the station 1 and station 2 are sending the 0 bit, and station 4 is sending a 1 bit, station 3 is silent here. So the data at the sender site are translated to -1, -1, 0 and +1. So -1 and -1 is for station 1 and 2, 0 is for the station 3, and +1 is for the station 4. So that you can observe from this diagram. Please take the screenshot of this diagram. So here you can see there are the 4 stations has been shown, and each station is sending a data. Suppose station number 1 is sending here -1, station 2 is also sending the -1 because both is sending bit 0. Similarly, the station 3 is silent here, so it would be sent the 0, and the station 4 is sending bit 1, so it is a +1. Now each station multiplies corresponding number by its chip. Chip is what? It is a orthogonal sequences that we have learned yesterday, which is unique for each station. So the result is a new sequence which is sent to the channel. For simplicity, we have assumed that all stations send the resulting sequences at the same time. There is no any time delay in between of the sending the data. So the sequence on the channel is sum of all 4 sequences that is defined already in the yesterday's lecture. So the data multiplied with the code, and it would be added to for all the stations in that channel. So in this diagram, that is same situation has been shown. So here you can see that this is the data is coming, that is -1, and then this is the chips for all 4 stations C1, C2, C3 and C4, that is having the pattern, and then it would be multiplied with the D1 C1, D2 C2, like D3 C3 and D4 C4, and then further it is sent through the common channel. Here all this multiplication has been added that we have learned yesterday, D1 C1 plus D2 C2 plus D3 C3 plus D4 C4, and it is the combined data has been sent on this common channel. And when you have to be see here, so each data would be added here. So -1, -1, then +1, sorry, 0, and then +1. So it would be become -1. Similarly, -1, +1, 0, -1, remaining is -1. In the third position, -1, -1, and then -1. So it is -3. Similarly, at the last, it would be remaining the +1. So in this way, this would be added and sent as a combined data on this common channel. Now, imagine the station 3, which is here silent, is listening to the station 2, and station 3 multiplies the total data on that channel by the code for the station 2. So which is +1, -1, +1, -1. So we would be see that station 3 would be got the data is -1, -1, -3, +1, that is multiplied with the code of the station 2, because station 3 is listening here station 2. So here we would be multiply the data with the code of station 2, and then it would be -4 upon 4, that is -1. It would be representing the bit 1. So in this way, any station could be listened to any station, and the resultant value of the data would be there. So in this way, you can see here how the communication has been established between the stations. Okay. Now, if you have to see the signal levels, the process can be better understood if we show the digital signal produced by each station and the data recovered at that station. Till we have just talking about the binary data. Now we have to represent this data in form of the signals. It is also very simple, and you can understood this concept through this diagram, where we have converted the data into the corresponding signals. So you can see here, so bit 0 by sent by the station 1 and 2, and station 3 is the silent here, and bit 1 is sent by the station 4. So if you have to see here, actually it is -1, so it is by mistake, it is bit 1 is mentioned, it is bit 0 actually. So correct it. Okay. So in this diagram, you can see that from the station 1, the chip or the orthogonal sequences are that is -1, -1, -1, and for station 2, the some other station 3 silent, so it will be 0, 0, 0, and finally it is this. Okay. So it is you can say D1, C1, D2, C2, and D3, C3, and D4, C4. So finally, this data would be come into the common channel. So if you have to be represent this data in the form of signals, it would be -1 means it is below the reference axis. All the data are -1, 4 bits. But in the case of station 2, it is -1, then +1, then -1, then +1. So it would be represented at like this. Then station 3, that is silent, so it would be remains 0. Station 4, +1, -1, -1, +1. Now the corresponding data that is available on the channel, that is the addition of all these 4. So it would be become this -1, -1 means -2 +1 -1. So finally it would be here -1. Then in this case again, this 2 be cancelled, but this would be -1 is there. Then in the third position, -1, -1, -1, that is -3, and then at the last one it would be remains the +1. Okay. So in this way you can represent the data digital signals of these 4 stations created by these 4 stations, and this interpretation is far better to understand as compared to the representation of data only. And now in the next diagram, we have to see that how the station 3 can detect the data sent by the station 2 by using the code for the station 2. So the total data on the channel are multiplied by the signal representing station 2 chip code to get a new signal. So the station then integrates and adds the area under the signal to get the value of -4, which is further divided by the 4, and it would be considered as a -1 means that is bit 0. So you can see here decoding, how that decoding has been performed. Because we have transmitted the bit 0, so we have to also decode this. So data on the channel is shown by the topmost diagram, and then station 2's code is, that is +1 -1 +1 -1, that is also represented here. Okay. And then inner product has been done by these two, data and the station 2's code, and that would be came as like this. And then the summing value would be, we have to be sum these two, so it would be came as -1, then again it will be goes to the +1, so it would be increased by the same amount, then again it would be come to the -3, and then again -1 means -4, so finally it would be reached to the -4, and then this will be divided by 4, and that we have already learned in the last lecture, that there is a total number of stations is 4, so it would be divided by the total number of stations. So finally we would be got the value is -1, that is corresponding to the bit 0. In this way we have sent that bit 0 to the transmitter, and then it would be decoded at the receiving end. So this is all about the code division multiple access, how the data has been transmitted through the CDMA technique. Now we have to be moved to the next topic, that is spread spectrum technique. So spread spectrum technique is an important form of encoding for the wireless communication. The spread spectrum technique was developed initially for the military and intelligence requirements. So what is the idea behind this? The idea is to spread the information signal over the wider bandwidth to make jamming and interceptions more difficult. The first type of spread spectrum technique is developed, that is known as frequency hopping, and after that some more recent type of the spread spectrum has been developed, that is called a direct sequence. But both of these techniques are used in various wireless communication standards and products. Frequency hopping and direct sequence, both are very important methods used in the wireless communication. This is the general model for the spread spectrum digital communication system. So you note down this diagram. So if you have to see in this particular structure of spread spectrum digital communication system, the input data is fed to the channel encoder that produces an analog signal, and this signal with the relatively narrow bandwidth around some center frequency, and this signal is further modulated using the sequence of digits known as spreading code or spreading sequence, and generally that is a pseudo noise generator. The spreading code has been generated with the help of PN sequence generator, pseudo noise sequence generator, and that would be added with this channel encoder output, that is a narrow bandwidth signal, and this spreading code would be in the modulator, product modulator, would be mixed up with each other, and that would be generate the signal that is having the very wide bandwidth, and that signal would be transmitted through the channel. And for that, the receiving end, first of all we have to do the demodulation, and again we have to require the same spreading code for the demodulation, that is again generated with the help of the PN sequence generator, and whatever the demodulated signal, that would be further decoded with the help of the channel decoder, and we have obtained the output data that is same as the input data. So this is a very simple description of this particular model of the spread spectrum that you can describe with the help of this block diagram. Typically, but not always, but most of the cases, spreading code is generated by the pseudo random number generator or pseudo noise generator, and the effect of this modulation is to that it would be increase the bandwidth or spread the spectrum, you can say, of the signal that should be transmitted. On the receiving end, same digit sequence is used to demodulate, and finally the signal would be obtained fed to the channel decoder to recover the data. So that we have seen through the diagram also. Now, what is the beneficial attributes of this spread spectrum systems, or what is the advantage of this? So there are the various advantage you can see. First of all, anti-jamming capability would be come into the communication system by using the spread spectrum. Interference rejections capability would be developed. Energy density would be reduced. You can apply the multiple access technique for your transmission in wireless communication. Improve the spectral density or efficiency. Then you can follow the multi-path protections also, and it would also provide low probability of the intercept, LPI. So these are the some benefits of the spread spectrum. That's why we have moved to this technique. Initially it was used only for the military applications, but nowadays also lots of the wireless companies would be using these techniques. And the most important is that it would provide a secure communication also. So if you have to be classify the spread spectrum technique, that would be, first of all, it is a direct sequence, DSS. So it is a average type of the spread spectrum. And second one is the frequency hopping, that is the avoidance type. Another is also used, that is time hopping and churn. But as per our syllabus, we would only discuss direct sequence and frequency hopping. Now, before going to the direct sequence spreading technique, we have to be first of all learn the pseudo random sequence generation, because that would be used in all spread spectrum techniques. So here you can see, you can note down this diagram of the PN sequence generator, where you can see there is a structure of the this is just like a shift register, where we have used the flip flop, D type flip flop, D0, D1, D2 up to the Dn-1, means n number of the flip flops are used here, that is start from 0 to n-1. And the you can see it is just like a shift register like structure. The output of one flip flop is given to the output input of the next flip flop, and that process has been be followed up to the nth number of the flip flop. And output of all the flip flops except output of all the flip flops is given to the parity generator, and the output of the this parity generator is given to the D0, first flip flop. So in this way, this is a you can say establish a feedback path, and all the flip flops having using the same clock, that is it is a synchronous type sequence generator. I hope all of you have noted down this diagram. So I will describe it in detail. A PN sequence generator, that is consists of the shift register, you can see, or it is also mentioned, and it is will be selected as the type D flip flops, arranged that each data input except the D0 is the Q output of the preceding flip flop. Except the first flip flop, all the flip flops is nothing but their inputs is nothing but the output of the preceding flip flops, and the input D0 is coming out from the output of parity generator. What is the parity generator? Parity generator is that is generally made up from the XOR gates, generates an output which is at logic 0 when even number of inputs are at logic 0, generates an output which is at logic 1 when the odd number of inputs are at logic 1. So depending upon the even and odd number of inputs, it is either in the logic 0 or either logic 1, output of the parity generator would be varied. The parity generator inputs are nothing but the output of the flip flop that we have seen through the diagram, and we have also shown a portion of each connections to the parity generator input as a dashed line in order to indicate that not all outputs Q need to be connected to the parity generator. Depending upon your the structure of the PN sequence generator, means you are using the 6-bit, 4-bit, 8-bit, 32-bit. According to that, you have to be select the value of the n here, and according to that, that much amount of flip-flop output will be connected to the input of parity generator, not required all the outputs. So the state of sequential system that is shown in the diagram is specified by stating the logic value of all queues of flip-flop, and during the course of a clock cycle, the state of the shift register remains fixed. But in general, state changes at every advance from one clock cycle to the next clock cycle. During that one clock cycle, it will be remains fixed, but when it will be shift from one clock cycle to the next clock cycle, this would be changed. So here we are using a register of n flip-flops that is having the 2 raised to the power n states from the output Q0, Q1, Q2 up to Qn minus 1, that would be 0, 0, 0 to the output is 1, 1, 1, 1, and it is clear that the hardware cannot generate a truly random sequence since it is a deterministic system. Generally, we say that the sequence is random in nature, but in actual, this is little bit deterministic in nature. That's why it is not called the random sequence. It is called a pseudo random sequence. It is also clear that whatever the sequence of the states through which the sequence generator progresses, the sequence will be repeat. That's why it is also a periodic in nature, and such is the case because each state is uniquely determined by the immediately preceding state. Thus, each time the generator arrives at some particular state, the subsequent sequence of states will be always the same. So what is the maximum length sequence? Means whatever the sequence generated by this PN sequence generator, what is the maximum length of that, but any sequence is there, it could be defined as L is equal to 2 raised to the power n minus 1. Suppose there is a 6 flip-flop, so it would be 2 raised to the power 6, means 64 minus 1, 63. After 63 clock cycle, it would be repeat the sequence. So that would be defined from this formula. The maximum length is L is equal to 2 raised to the power n minus 1. This is very important relationship. Please note it down. Now we have to see the properties of the PN sequences. So basically there are 3 properties we would be discussing short. First of all, balance property. So what is the balance property? In each period of the maximum length sequence, the number of ones is always 1 more than that of the number of zeros. This is basically a property that is called balance property. So always here number of ones is at least 1 times greater than the number of zeros. This is called balance property for each period of the maximum length sequence. For example, we have taken the maximum length sequence of the 63 clocks. So after 63 up to 63 clocks, if you have to count this is the odd number. So number of ones would be greater than number of zero by the 1. Means number of ones would be suppose 32 and number of ones would be 31. Second one is the run property. The run means the subsequence of the identical symbols, means ones or zeros. So whatever the sequence it would be generated, that could be having some subsequence of the identical symbols within one period of the sequence. The length of this subsequence is length of run. For the maximal length sequence generated by the linear feedback shift register of length n. So here you can define the number of runs. So the total number of runs is L plus 1 upon 2, where L is equal to 2 raised to the power n minus 1. So it would be 63 plus 1 upon 2 means 64 upon 2, 32. So 32 runs is possible, and these runs could be maybe either the length of 1, length of 2, length of 3. So in each period of the maximum length sequence, there are one half the runs of each kind of length 1. Means out of 32 runs, you can see out of 32 runs, 16 runs of length 1 and 1/4 of run of the length 2, means 8 runs of length 2. Similarly, 1/8 of the runs of the length 3, means 4 runs of length 3. Similarly fashion, 1/16 of the run of length 4. So 1/16 means 2 runs of length 4. 1/30th of runs of the 1/32 times of the runs of the length 5, means 1. Length 6 only 1, means run is 1, means suppose 1, the sequence is like this: 1 0 1 1 0 1 1 1 0, like. So here 1 is, after that there is a 0, so it is a length of 1. Then 0 is a length of 1, but here 1 is a length of 2. Here again 0 is length of 1. In this way we have to be count. We would be clear it from the practical that will be learned in the Friday. So third property is correlation property. So the autocorrelation function of maximum length sequence is periodic and binary valued, and this property is called the correlation property. So this is the third one property. So after learning the PN sequence, we have to be now move to the topic that is called direct sequence spread spectrum technique. Okay. So here you can see again this. So direct sequence spread spectrum technique is a DSSS method. In this method, direct sequence directly modulates the pseudo noise sequence or PN sequence. Let the data sequence represented by the here BE, and this data sequence has been just a minute. This data sequence has been represented by the BE not, here it is BK, and this data sequence is converted into the bipolar or polar enlarged waveform, that is BT. That is, you can say BK is equal to 1, means BT is equal to +1 volt. BK is equal to 0, means BT is equal to -1 volt. That is a polar enlarged waveform. And let CK denote the pseudo noise sequence that is used for the modulation here, and CT represent the polar enlarged signal generated by the CK. When you apply the PN sequence to this polar enlarged signal, so it would be modulated signal would be CT here, that is a polar enlarged signal generated by the CK. So what is the CT is here? When CK is equal to 1, CT is equal to +1, and CK is equal to 0, CT is equal to -1. So on the taking of this knowledge, you can also give the equations numbers, equation 1, and this is your equation 2, that will be further discussed. Direct sequence spread spectrum transmitter. So in this case, this is the diagram and the structure of the direct sequence spread spectrum transmitter or encoder. Here you can see the data signal BT and PN sequence CT are applied to the product modulator. And that would be generate output of this modulator that is having very wide spectrum, because it is multiplied with this particular PN sequence. The MT is having the output of this product modulator that is having a wide spectrum, means bandwidth will be increased, and the spectrum of this signal is quite high, compared to the narrow band signal BT. BT is having the very small bandwidth, but when it would be multiplied with the PN signal, it will having the product is having very high bandwidth, and this signal would be further applied to through the channel, and that would be applied to this adder. If I have to see here, there is signal MT would be added, and along with that, when it will pass through the channel, there is some interference would be added, that is represented as the IT. So it is here baseband channel, and then whatever the product of this that would be RT is received by the receiver. That is a noisy or a noisy version of this MT. Okay, so I hope all of you have noted down this diagram. So further you have to see the output of the modulator is a wide spectrum, and the message signal is represented as here the output of the product modulator, that is here MT is equal to CT into BT, and the pseudo noise signal CT is wide spectrum signal, it is multiplied with the narrow band BT, that would be make it again MT as a very wide spectrum, and this MT would be transmitted through the channel where it would be interfered by the some interference signal or noise, and during this IT would be interfere the signal MT, generate the signal RT. So RT is what? It is MT plus IT. Okay, this is question number 4. So this interference would be added here during the transmission through the channel, and you can also write the RT it as in terms of CT BT, because MT could be from the equation number 3, it is CT into BT. So this is you can write written as a CT into BT plus IT. This is equation number 5. So that signal has will be transmitted through the direct sequence spread spectrum transmitter. Now this received signal would be, you can see here how the pattern of the signal that is shown through this graph. So this is your data signal BT, that is a NRZ signal. Okay, and this is a polar NRZ signal for the binary 1, when BK is equal to 1 is it is +1, and when BK is equal to 0 it is a -1 volt. Okay, and that is having the bit period of TB. Now this would be mixed up with this PN sequence, that is CT, that is again a polar NRZ signal but is having the higher frequency. So the bit period is here, TC is here, NTC total. So n number of the bits would be there, and then it would be multiplied applied to the product modulator. Output is MT. So you can see here +1 -1 -1, then +1 +1 +1, here -1 +1 -1, and here in this particular case +1 +1 +1 up to this point. And but when your data signal would be reversed -1, so it would be again opposite function, -1 -1 +1, and then like this. So this in this way MT signal would be generated, that is product of BT and CT. But at the receiving end we are receiving the RT, that is the summation of MT plus IT. So this is the receiver structure of that sequence DSSS receiver. So please note down this diagram. Here you can see that the received signal RT is again applied along with the PN sequence CT to on this product modulator, and output of the product modulator is a ZT is here, that would be applied through an integrator of the limit of 0 to TB dt, and further we have to be generate a signal, that is V, and it would be passed through the decision device that is having some threshold value. If B is greater than 1 means it will be considered as a binary 1. If B is less than 0, it will be considered as the binary 0. But through whole this structure you have to remember that this is a baseband transmission. There is no passband. It's a baseband transmission. Okay. So mathematically you can also represent this whole structure of the receiver where we have to use the locally generated PN sequence. That is exactly same replica of the PN sequence used in the transmitter side. So the output of the product modulator is equal to the received signal, noisy signal RT into CT. That is nothing but your ZT. So ZT would be your equation number 6. Then substitute the value of RT that we have described in the equation number 5 in the above equation. You would be got CT C square T BT plus CT IT. RT is what? It is CT into BT plus IT. So it would be multiplied with the ZT here, and the ZT would be modified. That is presented through the equation number 7. So from this equation number 7, you can see that what is CT? CT is a polar energetic signal that could be +1 or -1. So C square T is what? It would be always +1. So you can consider here in the equation number 7, C square T is equal to +1, and that would be now modify again the ZT, that is BT plus CT into IT. That is mentioned here. So ZT is equal to nothing but BT plus CT into IT. So this would be equation number 8. So thus at the output of the multiplier, the data signal BT is reproduced with the noise CT into IT, because IT is here interference. And we know that CT is a wideband signal. When it is multiplied with the noise IT, the product CT IT, it is also a wideband signal, because it is PN sequence. It is multiplied with this PN sequence, this interference. It would be the resultant signal would be again a wideband signal, means bandwidth is very high. And this signal would be further pass through the integrator. So the bandwidth of CTIT is very much large as compared to the BT, and the resultant signal ZT is then passed through an integrator, which integrates over a 1 bit period, that is TB, and this integrator acts as a here low pass filter. So removes the wide band noise CTIT, because it is acting as a low pass filter. It would be only pass the low frequency or low bandwidth signals and reject the high bandwidth signals are there. So in this case, the whatever the resultant signal would be generated, that is V here, and this would be further passed through a decision device that compares the output of integrator with a threshold of 0, and it takes the decision in favor of the symbol 0 when V is less than 0 and symbol 1 when the V is greater than 0. So in this way, we have seen that how the diode sequence spread spectrum using this technique DSSS, we have to be transmit and receive the signal, and on the basis of that we would be learn the DSSS with coherent BSK in the next lecture, BPSK signal with DSSS technique. The time is very less, so fill up the attendance on the chat box. In the next lecture we will be discuss the BPSK with this DSSS technique, and then we have to also learn the frequency hopping. So in the next Friday during the practical session, I would also take this lecture of the data communication. So we have the 2 lectures remaining, Friday and Saturday. So we would be trying to cover the syllabus. If it required, we would take 1 extra lecture also. So join whenever I will be put up the notice on your group on Friday for this lecture of the data communication, and within that we have already learned the PN sequence in theory, so we will discuss the practical in short in 15 minutes. Thank you all of you for attending the lecture. Thanks a lot.